Hello, everybody. Thanks for joining this webinar. We're going to talk about DTLS version 1.3. So first of all, let's try to explain what is DTLS in just one easy sentence. So DTLS is just a very easy way to provide security to datagram-based application. I think some of you will be familiar with TLS. So TLS is an added layer of security on top of TCP. So DTLS is for UDP what TLS is for TCP, basically. Okay, let's see the agenda of today. So we will cover some basic about DTLS, and then we will see some comparison between the older version, the 1.2. We will see the improvements of the 1.3 and why it's better to move to the latest version. Then we will see some example on how to use DTLS in our wolfSSL library, and then some small hands-on on how to plug in DTLS in your UDP application. And as our last point, we'll cover some new features and future features that we will add to our implementation in the foreseeable future. We'll end everything with a Q&A, so please use the Q&A box and I'll reply at the end of the session. So let's start with the basic. First of all, let's try to understand why there is a number missing in the version of DTLS. So basically, the first version of DTLS, the 1.0, was based on TLS 1.1. So there is this mismatch between the two versions, because as we're going to see in a few slides, DTLS is built on top of TLS. So this mismatch of number creates some confusion, so they decided to skip a number when they developed DTLS 1.2 that was matched with TLS 1.2. And so we don't have any DTLS 1.1. And the subject of this webinar will be the latest version of DTLS, that is the DTLS 1.3, that is defined by the RFC 9147. So first of all, let's check why we need DTLS. Why we don't just why can we use TLS? So basically, the main problem with TLS is that it requires a reliable and ordered communication channel. So basically, this is provided to TLS by the TCP layer in most of the cases. So in order to provide this reliability and this order of communication, TCP, of course, need to do some housekeeping. So it needs to keep a buffer. If a packet came unordered, they need to reorganize the packet. It needs to wait for transmission if some packet get lost in the network, and so on and so on. And unfortunately, this very nice property of being reliable and ordered comes with a price, and this price is some overhead in the latency, in the bandwidth, and in some other problem that can cause some very big delay. And there are some use cases that cannot afford this overhead, like real-time streaming or virtual private network application, online gaming, or some devices that are very constrained, both maybe in battery power or in their resources. So there's sometimes some use cases that you cannot really afford this overhead and this latency that comes with TCP. So what's the idea then behind the TLS? So the idea is to just add a minimal delta to TLS so that it can be used over a protocol, over a layer that doesn't provide these guarantees. And this has two very big advantages. So the first one is that we reuse a well-established crypto system that is already used from years. So we can be kind of more can be trusted a little bit more because it was tested in the field for already some years. And then, of course, because if we adjust a minimal delta, so we can reuse most of the TLS implementation. So the cost of providing a new DTLS implementation is small compared to creating a new protocol from scratch. So, but how DTLS accomplish that? So the main point about TLS requiring a TCP protocol is because there are some message in the beginning of the session, the message that are used to create the cryptographic primitives and cryptographic secrets to then um, encrypt the connection basically and the authentication. They need to be provided in order, of course. Um, so the idea is to have the reordering or retransmission, but only for this type of message. So we add retransmission reordering only for the handshake message. And we don't provide any guarantee of delivery of or ordering instead for the application data. Because we don't provide any guarantee, because DTLS doesn't provide reliability for application data, then we can miss some packets. In order to decrypt a packet, we need to know its sequence number because it is needed for a successful decryption. So on top of implementing retransmission and reordering, DTLS also add the sequence number into the packet itself. So we can lose package and we can lose some packets and we can still be able to decrypt the message. So these are the two main difference between TLS and DTLS, basically, on a very high level overview. So just to recap, when DTLS is a good choice. If I want to secure a UDP-based application, because if I have a UDP-based application, chances are that I cannot afford the overhead of TCP. For real-time data communication that cannot afford delays, also with devices that they are tight resource limits, because also the implementation of TCP, it can be quite big. So if I have a very tight constraint in memory, it being runtime memory or code size memory, then DTLS can be a choice to reduce these to consume less resources. And of course, for lightweight protocol. So usually now I will just show you a small comparison when I use an application with unsafe communication. So usually there is some sensor, some IoT that collecting data. This data is basically packed in a proprietary protocol and then is sent over the network using UDP. Of course, all the message in this kind of scenario can be manipulated, can be intercepted, can be also spoofed. So DTLS usually is plugged in this layer of the stack. So the device still collects this data, it still use its proprietary protocol, but then it's framing in this proprietary protocol in DTLS, and DTLS provide authentication so that you are sure that who is the sender of the data, confidentiality so nobody can intercept and read the data, and of course integrity, so nobody can manipulate the data without being noticed. And of course then DTLS will go over UDP as before. So now that we covered some basic of DTLS, we are going on over some comparison between the older version and the new one, just to see what changed. So first of all, we have to remember that DTLS builds on top of TLS. So DTLS 1.3 builds on top of TLS 1.3. So all the improvements of the TLS 1.3 version are get it for free in DTLS 1.3. Especially is a modern, a faster, a safer cryptography, and I think very important nowadays is quantum resistant. You cannot use quantum resistant algos on older V1.2 DTLS because it's not supported. And this is just already, this is a very good reason to move on a newer version. So let's go over that points in details. So first of all, it's safer. It's safer for several reasons. I'll go over some of them. So first of all, in TLS 1.3 and so also in DTLS 1.3, older and unsafe algos were removed. So this is a list of all algorithms that get removed and cannot be used in TLS 1.3. Also, it's safer because by default, it always enforces perfect forward secrecy. Why this is important? Because it covered on this attack scenario that I'm showing here. So basically, if you are reusing the same key always for encrypting your data, then somebody can keep collecting your communication just in the hoping that in the future, maybe looking in some discarded hard drive or some other way, this key gets compromised so you can decipher all the accumulated communication of the past. If you instead create a new key every session and this key can delete it just after the communication, so you get something that usually is referred as ephemeral key, then you are kind of better for this kind of threat. And in DTLS 1.3, this is the default, and you almost never can do reuse the same key for new session. There is just one small way that you can use pre-shared key in a way that is not enforcing PFS. But other than that, all the cipher suite that are negotiated between the server and the client will use for forward secrecy. It's also modern because in the past, of course, so TLS and DTLS will provide both confidentiality and both integrity. So these two things need to be combined. So usually you provide some sort of code that it's called authentication code that it tells you that the data is not manipulated. Unfortunately, encrypting before doing the MAC or the other way around created a lot of confusion in the past and some vulnerabilities. So there is not a very good. There are a lot of trade-off of doing one before and doing the other. It's hard to get right. So newer algorithms just do both operation at the same time in something called authenticated encryption with associated data, AEAD. And in TLS, this is the only cipher mode you can use because the older mode, it was removed. So these are some example of this kind of cipher. So it's also safer because more part of the handshake is encrypted compared to TLS 1.2. We're going to see here, this is like an handshake. So the handshake is the first part of the of a connection when the client and server negotiates their cryptographic secrets. And as you can see, the client here send a client hello. This is in clear. The server always reply also with their server hello, with their public key, with using server key exchange, and the certificate of the server for authentication, and all these parts is in clear. The first message that is encrypted is the finished message, and then of course the application data. Compared to the refactor that was done in TLS 1.3, you can see here that that after a client hello, the server reply with the server hello, but then all the remaining part of the handshake, it will be encrypted as well. So more part of the handshake is encrypted for an increased security. And of course, application data is also encrypted. But it's also faster. It's faster because it's faster in TLS 1.3 to start sending data. Let's see that with a comparison of the two and shake. So here on the left, you can see the client that send a client hello and the server that reply with this bench of message. Okay. And this is already one round trip time. Okay. A message needs to travel from one side to the other, and another message needs to be sent from the other side from the server to the client. Then the client need to send its own public key again. So the client send client key exchange, change per sec, and finish it. And then the server need to reply back again. And just now you can start to exchange data between the client and the server. But in 1.3 instead, you see here that the client sent the client hello to the server. The server reply with server hello and their encrypted extension, certificate request, and so on to the other message. And after that, the client sent its own certificate and definition message, but as the public key were already exchanged in the client hello and the server hello, you can already start to send application data. So you need just one round trip time to start communicating between client and the server. The server can even do better because the public key of the client, it's already in the client hello. So it can start sending data already in together with the server hello and the other message. The only problem is that at this time you don't you still don't have the server hasn't authenticated the client yet. But this sometimes from some use cases is okay because like in HTTPS, usually the client is authenticated in the application using a web form and not on the TLS with certificate. So sometimes it can be used. And you can see here in this graph how TLS 1.3 can be faster when the latency of the network increase, of course. So you can get a very pretty good advantage and set up the connection quicker using TLS 1.3. We can even do even better because when you're resuming a connection, that means that you already made a connection, then you want to save some of your cryptographic data that you are negotiated so you can restart the session later faster. Or if you set up the client server with an already pre-shared secret key, then the client alone can start sending encrypted data already with this message. Something called zero RTTT app data, or also known as early data. These data have not the same guarantees of the other data, unfortunately, but it can be really useful if you really need fast response from a server. And of course, 1.3 comes with quantum resistant support. So it supports with the MLCAM, so to exchange a secret for authentication with the DSA, also with XMSS and LMS. And in wolfSSL, we have all native implementation of the algorithms, and they are all supported in our DTLS and TLS 1.3 version. And we, of course, support also hybridized modes where you can combine both a classic algo and a quantum resistant algo. The rationale behind that is that in this way you can combine the strength of a classic algo that it's well tested on the field, so we can kind of trust because it's a lot of years that is around and nobody break that. And you can avoid to rely only on algo that it's supposed to be safe, but it's not is not in the field for uh, the same amount of time of the classic one, so you can kind of trust less. But there are also some improvements that were specific to the DTLS aspect of the protocol. And the DTLS specific improvements make DTLS safer, faster, and more efficient. So, first of all, as I said before, the sequence number are explicit in DTLS. In DTLS 1.2, this record number were in clear text. Now this message sequence number encrypted. So it's better because you can avoid some traffic analysis. So it's better from privacy. It's more efficient because they are modified the header, so the header now is not the older plain text header. Can be very small because you can avoid to put the length, and you can use 8-bit sequence number, so it can be as small as just 2 bytes, and this is kind of nice. And also in DTLS, they had a new message to explicitly acknowledge make the acknowledgement between the server and the client of some of the message explicit. We will see with a simple example how this can help. So let's say that the client sent 3 messages to the server, the blue, the orange, the yellow one, and the orange one get lost. So what the server can do is to send an ECK message with saying, well, I received the yellow one and I received the blue one. So now the client can just send the orange one. So this saves bandwidth for sure, because without this message, the client will need to retransmit all 3 messages and not just the one that was lost in the network. But also, it shortcuts the retransmission timer, because when using the hack, you can tell the client, well, there's something happened, and you lost some message, so please resend them. So it's faster and useless bandwidth, and this is like a graph that compares the two. It's also nice because in DTLS 1.3, the connection ID, that is a feature that was already available for 1.3, but 1.2 is built in. So instead of having a kind of an extension with another RFC, it's built in the protocol. Connection ID is a very nice feature that basically decouple IP address and port from the session. So this is useful if you have a device that change IP address often, and you don't want to do an handshake again every time the IP change. Think about very long-lasting session with devices that are very battery power constrained, so they want just to wake up sometimes, send some data, and go sleep again, and maybe for years. So they don't want to wake up and need to do a new handshake just because the IP address changed in the meanwhile. So with connection ID, what you can do is basically attach a label to the session, so that this label can be used instead of the IP address to recover with the session, which session belongs the message. So another nice thing is that now in DTLS 1.3, you can perform a return routability check using hello retry request message. This improve the robustness of the server against denial of service attack. How does it work? Basically, the client send a client hello to the server, and the server send an hello retry request with a cookie. So the cookie is just a number, and the client replies back. And this shows to the server that the client can receive message. And this is very important because otherwise, some of these message can be forged and send to the server that will send all the reply back to another client, and this will kind of make the server an amplificator for my denial of service attack. And this hello retry request somehow mitigate the issue. In wolfSSL, all this part in the beginning is stateless. And this is nice because the server doesn't have to allocate any resources to do this hello retry request with cookie. This is something that deals with DTLS and post-quantum cryptography. So in post-quantum, one of the problems is that the public key, let's call it public key, the encapsulation key, and the ciphertext is way bigger than the encapsulation key and the ciphertext are basically what is transferred on the wire. Is way bigger compared to standard classic key share algos. So this can be a problem because even if DTLS can fragment message, because a message that doesn't fit in the maximum transmission unit of the UDP can be fragmented over several fragments and then reconstructed on the other hand. We just saw that we want the client hello, the first client hello, to be stateless, and fragmentation and stateless are hard to do together, very hard. So in wolfSSL, what we do is that the first client hello is without the key share. But of course it has supported groups. So it advertised that the client hello advertised that won't use, for example, MLCAM, but doesn't provide the encapsulation key. And at this point, the server sends back the hello retry request with a cookie, and the server can also say to the client that it will be able to use the MLCAM. And at this point, the client send a client hello, but now that we are not stateless, we can fragment this client hello. So this client hello can come with several datagrams, will be reconstructed at the server side, and we can recover the post-quantum bigger key share on the server. This can be enabled. So to enable PQC, we will see later how to build the DTLS wolfSSL with DTLS support. So we go over these commands later, but just as a note to, if you want to enable this post-quantum, you have to be sure to enable, of course, Kyber, that is MLCAM, and then you also need to enable the fragmentation of the client hello with these flags. The slide deck will be available after the webinar. So the version of the protocol can be negotiated. So both you can have a client or a server that supports both versions at the same time, and then it nicely fall back with when speaking with peer that only speak about the older version. And this allows for a gradual upgrade of your ecosystem when peer of different version can coexist. So now that we do all of this information with DTLS, let's see how we can run DTLS using wolfSSL. So first of all, wolfSSL is an open source library, it's on GitHub, you can just download it and build it. So these are very basic commands. Many of you are familiar with this kind of command. So you can clone the wolfSSL repo. You can start with autogen script. It's just a small script to create the auto tool to update the auto tool files, and then you can do the configure. It's configure and make typical commands. The important option to enable to use DTLS 1.3 are enable DTLS and enable DTLS 1.3. Configure has a lot of more configuration option. You can use --help to look over them. Once you build our library, the library has two very good a very good client and a very good server example that showcase all the features that are built in the library. They are under example client and example server. This is the less amount of option you can use. We'll use a local host port, if I remember correctly, 1111. And these are the only two options that you have to use to be able to have a DTLS 1.3 connection. So you have to use -u to tell him to use UDP, so go over DTLS, and then you want to use version 1.3 that it's enabled by using -v4 in our example. You can use --help. You can see a lot of other options and flags you can you can play with them. So if you run that command, you will see that the example exchange a very small message. The client send hello wolfSSL, and the server reply with I refresh user. And you can see here that the version uses DTLS 1.3. You can see also that the Cypress suite uses this TLS with a EAD method using the SHA-256 and the curve used for authentication. So if you want, you can run Wireshark on the side, and you can see, of course, it's an encrypted communication, so you only can see the plain text part, the clear text part of the handshake normally using server and client. And in order to correctly decrypt the protocol version in Wireshark, you need Wireshark at least version 442. You can go over the server below and you can see go in the handshake protocol. Please note that both in the handshake and in the record layer, the version reported is DTLS 1.2. This is basically the same in TLS 1.3. The problem was that maybe it's not a good time to talk about that but when they deployed TLS 1.3, a lot of middle boxes stopped working. So in the TLS 1.3 asked to stick with version 1.2 reported in this field of the header of the message. And then they use another extension to negotiate the actual version used. And you can see in the extension that the version used is instead DTLS 1.3. You can see the cyber suite, the curve used for the authentication, for the key share, and then the supported version. Okay, now if you also want to see the other message, you can enable the keylog export. If you configure the library using this flag, of course, do that just for debug only. The key of every session will be exported on a file called sslkey.log. And then you can set up in Wireshark to use the keylog file, and Wireshark will decrypt all the handshake and the application data as well. So you can use for debugging, and you can look in the handshake message. And you can see here, I will compare the handshake with TLS 1.3. You can see the certificate is fragmented because it doesn't fit in an MTU compared to the 1.3. And also you can see an acknowledgement message that is, of course, specific to DTLS. Okay, so now let's go briefly over what you need to do to kind of modify a very simple UDP application to use DTLS. Of course, this is So as we said before, we need to add this layer before going over the network. So let's go over this kind of oversimplified example. So when you have an UDP application, you create a socket. Of course, you use sock diagram because you want to use UDP. And after you create the socket, you can recover your data, you pack your data in your proprietary protocol, and so on and so on. And then you communicate with the other people using send to and receive from. And then when you have done, you can just close the socket and close the application. So the first thing we have to add to use DTLS is some initialization. So first of all, it's not shown here, but you will initialize the library with wolfSSL init. Then you need to create the context. The context will be something like a blueprint to create session. And as you can see here, you create the context using wolfSSL context new, and you provide wolfSSL DTLS client method because we want to that this part of the application to be the client side. And please notice that we are using wolf DTLS, so this will allow us to use DTLS. Then, of course, we have to load our root CA to verify the server certificate. And you can also check the documentation of wolfSSL. This is not DTLS specific. And then you create the SSL object that is associated with the session with wolfSSL new. So you have this object, the SSL. So this is like the DTLS setup. Then you open the socket as usual using sock diagram. But after opening the socket, you have to set up some parameters of the DTL in the SSL object so that we know first of all, like we have to set the server address, so we know where to send a message to, so the server address, and we do that using wolfSSL DTLS set peer. Of course, this is kind of different compared to TLS because TLS is using is using TCP, and TCP is a connected socket, so you already know your endpoint, but it's not the same in DTLS. So you call wolfSSL DTLS set peer. Then you also associate the socket with the SSL object using wolfSSL setfd, and then you have to do the handshake. So you have to call wolfSSL connect. We are on the client side here in this example, so we'll send that client hello to the server, and the handshake will start beginning. And if the handshake completes successfully, this function return wolfSSL success. So we did the setup, we now did the handshake. Now we have to communicate. So when we have to communicate, we cannot use just send to and receive from. We exchange that using wolfSSL write if we want to send something. So, and wolfSSL read if we want to receive something. Of course, wolfSSL write will encrypt the message and send the message encrypted, while wolfSSL read will receive and decrypt the message. As with send to and receive from, we are on datagram socket, so there is no guarantees that this data get delivered, and there is no guarantee that this message is arrives in order of that the order is preserved between the sending and receiving. And there is also some cleanup. If we want to be nice with the other P, we can send them an alert. So saying I'm closing the connection with wolfSSL shutdown. And then I will clean up the memory using wolfSSL free and wolf context free. So this is more or less the oversimplified example on how we can add DTLS. So now let's go over some news. In wolfSSL, we added support for connection ID for both version 1.2 and version 1.3. This was a feature requested a lot of time, so we have now fully supported. We supported for 0.5 message, so the server can reply after the client log with the server log and send some data to the client. We made some very good improvements in server demultiplexing. We have a very good example, so you can use now connection ID to decide you can get a message from a SOC, and even if the IP address is changed, you can look at the connection ID, and then you can use a new API to basically process this message in the appropriate SSL object. We added more interoperability tests. Other libraries are keeping implementing in DTLS 1.3 as well, like libNSS. So we are doing more interoperability tests with them. There are some David Benjamin, a researcher at Google, found several problems with the current RFC, and we are addressing them in our implementation. This is more or less a work in progress. We are also looking at a feature that will allow to parallelize the encryption and the decryption of the data. This is also a work in progress. And we also did several fixes that are either in progress under review, or they're already merged in our master branch and will be available in our next release that will happen very soon. You can see here there is a link, of course, of the example. You can find it in the slide decks that you can request after the webinar. And also, there will be more example at this repo of example. You can go look on the DTLS director. There are several examples for both for 1.2, and for 1.3, client, server, multiplexing, etc., etc. So just to conclude, DTLS 1.3, a faster, safer, cutting-edge, post-quantum resistance way of doing encrypted communication. There is little on the chain to migrate from DTLS 1.2, and is full supported in wolfSSL. wolfSSL, I remind you that it supports a broad range of microcontroller, operating system, development environment, bare metals, and whatever. Our engineers are always available to answer technical questions. You can always send an email either to facts@wolfssl.com or to support@wolfssl.com. And of course, it's open source. You can start your evaluation, your development right away. So with this, I end my webinar and I open to your Q&A.
Thank you, Marco. To start off, is there a limit on the maximum data size that we can send in one message?
Yeah, so usually the limit is in the UDP protocol more than in the TLS protocol. I mean, DTLS and TLS have a maximum size that I don't remember now, but usually the maximum transmission using maximum transmission unit is the limiting factor here. But for regarding the handshake message, they get fragmented in the library itself. So wolfSSL and the DTLS protocol fragment the handshake message. For normal data application, you need to fragment them on yourself on the application layer.
Wonderful. How does DTLS handle session resumption, and what risks does this introduce?
Okay, resumption are handled basically the same way are handled in TLS 1.3. So with session tickets. So when you do when you do a session for the first time, then the server can give the client a ticket, and this ticket it's of course there is some cryptographic material that can be reused to shortcut the handshake in the next session, and so to do this resuming. There are no risk. The problem is that sometimes the only thing to note is that the server wants to be stateless in processing the client alone. So even if it's resuming, it may want to send back an error retry request to the client. But this can kind of slow down the assumption that it's supposed to be very quick. So in wolfSSL, you can disable that, but of course, then you are more exposed to some denial of service attack. It's kind of a trade-off that you need to take in consideration between security and performance.
Awesome. How does DTLS handle replay attacks and what mechanisms are in place to prevent them?
DTLS, it's similar to DTLS 1.2. They have a sliding window. So if you just take a message and reply the message to the application, the record explicit second number, as we said before. So you can always check if you already received that message or not. And if the message is too old, you will just discard it because you have, of course, to trade off between the memory you want to use to uh, keep track of the message you already received.
Wonderful. Last question here. How can an application check whether the application data is received or not?
Well, unfortunately, as DTLS does not provide any guarantee about the application data, the application needs to cares about it itself. So you need to develop that in your application.
Wonderful. Well, thank you, Marco, for hosting an informative webinar. Thank you to everyone for joining. I will email a copy of the webinar recording and PDF slides. Oh, there's a few more questions. Do you have time,
Okay,
Marco?
of course.
Does all the callback options available for normal TLS setup available for DTLS? And is there anything that is not supported?
Everything is supported. Everything that we support in wolfSSL, it's supported also in DTLS. So yes, it's supported.
Wonderful. If data is lost in UDP, are there much use case of this in automotive?
Yes, sometimes you want to collect sensor using UDP maybe for the automotive to talk with some backend server, and you don't care if some data is lost. So you want still to have the data protected, but if you lose some data, it's okay. So this can be an use case, for example, that you want to collect some telemetry data. If some data is lost because of network problems, you don't want to keep and resending this maybe data that are already stale. But you don't want neither that everybody on the network can look at the data, or that the data can be forged or are not authenticated. So it depends on the specific use case. As always, you can always send your specific question to fax, so we can deal with the different use case better.
Wonderful. Okay, as I was saying, I will email a copy of the webinar recording and PDF slides, and you can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at fax@wolfssl.com. Thank you again, and we look forward to seeing you on April 16th for wolfSSL solutions for the AMD Xilinx UltraScale and MP SoC and Versal. Thank you all.